In this first video in the quantum computing playlist, where I'm going to attempt to explain quantum computing from the ground up, I'm going to go over complex numbers in this video. So that in the next one we can use complex numbers to explain the basic tenets of quantum computing. So what is a complex number? So you could have some complex number, C, and what it is it's just a number that's specified by both a real and imaginary part. And these numbers A and B are just ordinary real numbers that we're familiar with. But this I, which is equal to the square root of -1, turns this term into an imaginary number because there's no real number that can square to -1 or any negative number for that matter. So a complex number is just a number that has a real and imaginary part. And since we're using two numbers to specify our complex number, it's useful to think of all the complex numbers as points on a plane, right? Where the y-axis, we can dedicate it to the imaginary part of any complex number, and then the x-axis will be the real part. So if A is somewhere along here, and then B, say, is up here, then our point C, which equals A plus BI, will be plotted over here. And a complex number also has a related number, or a related complex number called its complex conjugate. And we denote that by putting a star over the complex number. And the way these two are related is just by flipping the sign of the imaginary part. So wherever you see an I in your complex number, if you want to find its conjugate, you just flip the sign. So that will look like -b down here, and then C star is going to be over here. And another useful thing that we can define about a complex number is its length. Since we're plotting this on a plane, it has a certain distance from the origin, right? And say we'd like to know what this length is. And this is pretty interesting because you can just use Pythagorean's theorem here. We just have a right triangle. We have this x-axis length and this y-axis length, which is A and then B. So if we want to take the length of our complex number, which we do by putting these bars next to it, it's just the square root of A squared plus B squared. Or this can be rewritten as C times its complex conjugate. And you can multiply that out to see for yourself that this is what you're going to get. Okay, so now these complex numbers are beginning to resemble sort of vectors in a plane. It would also be really helpful for us if we could not specify both its part on the real axis and its part on the imaginary axis, but instead specify just its magnitude and then its direction. But how are we going to specify direction? Well, ideally we would do it with some angle. We'll call it phi. And there's a really neat way of representing complex numbers, but in order to do it we need to make use of this formula called Euler's formula. And this is just one of Euler's formulas. He had many. But this is perhaps the most interesting one. And what it is if you raise e to the power of I, which is our square root of -1, and then multiply it by some angle, right? And for now, let's just assume phi is in between 0 and 2 pi. Then what he said is that this is equal to cosine phi plus I times sine phi. And this is this is helpful to us because the first thing we should notice about these, well, it's just a complex number for one, because it has its real part and its imaginary part. And further, the length of any of these types of complex numbers is always 1. And how is that? Well, we can just use our formula for the length by squaring its real part and then adding it to the square of its imaginary part. And the simple trig identity will tell you that this is equal to the square root of 1, which is equal to 1. So all the points from from 0 to 2 pi, specified by this angle phi, is going to draw out a unit circle in the complex plane. And that's good for us because we can use these points along the unit circle to specify an angle or a direction for any given complex number. So say we have some complex number all the way up here, we'll call it C prime, and it has a pretty big magnitude, it's definitely greater than 1. And let's say its magnitude is just, 5 or something. And then on top of that, it has this angle here, we'll just call it theta. Then we can write C prime as e to the I theta times 5. Because what happens is e to the I theta is going to be this point, and then we just scale it up. 5 is not a good number here because this doesn't look like 5 times 1. It looks like maybe 2. So we just scale it up by 2. Right? And this might seem strange at first, like why would we write a complex number this way? But it turns out to be quite useful. And in fact, in quantum mechanics and quantum computing formalism, all these complex numbers with modulus 1, which is specified by e raised to the power of I times some angle, they're called phases. And this would be the phase angle. Because I'm going to start referring to these phases a lot, so it'll be useful to know this. Okay, so now that we've gotten complex numbers out of the way, in the next video, what I'm going to talk about is something called probability amplitudes. Which is perhaps the most important thing, or at least the thing that encompasses almost all the weirdness of quantum mechanics and how quantum mechanics differs from classical everyday physics and intuition. It's these probability amplitudes. And of course you can tell there's some relation to everyday probabilities, but as you'll see in the following videos, these act quite strangely in quantum mechanics.